Okay, fantastisch. Ja, sehr gut. Ja, ja.
Okay, welcome everybody to today's colloquium. I'm very happy to present you Stephan Stadler, currently from the Max Planck Institute in Bonn, but on his move almost already in Paderborn, where he will start a new position this fall. Yeah, it's a pleasure to have you here. He's working in the area of geometric analysis and metric geometry, and today he's going to present his work on minimal surfaces, isoperimetric inequalities, and non-positive curvature. The stage is yours.
Thank you. Thank you so much. Thank you for the invitation. It's a pleasure to be here. It's an honor to speak here. And it's true, yeah, I work in geometry or metric geometry, but I'm not going to assume anything. I'll try to address kind of everybody. And my goal for today is to maybe explain what these three topics that appear in the title have to do with each other. There's a classical relation. This, I hope that I can explain to everybody. But then, of course, I want to move on and tell you something about my actual research. This story begins. Oh, no, I don't even need that. There's no title for some reason. Give me 1 second. This is the starting point. So the classical isoperimetric inequality in the plane. And I'm pretty sure that most of you, probably everybody, has seen this before. As a reminder, suppose you have a Jordan curve, gamma, in the Euclidean plane. And then what the classical isoperimetric inequality tells us is that there is this fundamental relation between area and length. So if you start with a Jordan curve, then we know by Jordan's theorem, it decomposes the plane into two connected components. One of them is bounded. It's called the associated Jordan domain, omega. And, this is the mistake. Okay. Omega, and there's this relation. So the area of omega, in this picture, omega is this bounded component. The area of omega is controlled by this particular constant times length squared of gamma, and the constant is not arbitrary, it's actually a sharp constant, namely equality in this inequality holds precisely for round disks. So 1/4 pi is the ratio of the area of a disk by the square of its boundary length. There's many proofs of them, of this result, beautiful proofs, and I'm sure most of you have seen one. I'm not going to give one now, but I will prove something similar later on. So once you have such a fundamental relation, you want to see, how much can you take this? Does this hold in more generality? A natural thing. So in the plane, I actually have no idea how to ask a similar question, right? A related question. There are some related questions, but nothing as natural as this. However, if you move up a dimension, or let's right away jump to dimension n, so the title is almost the same, but now we're not in the plane, but we're in Rn, then the same result holds, namely, if you take a bounded domain, omega, then the n-dimensional volume of this omega is controlled by the boundary volume in this way. And again, this inequality is sharp, namely equality holds if and only if you look at a round ball. So Cn is this explicit constant, okay? So again, there are many proofs. You can use symmetrization. There's a nice proof using the Brun-Minkowski inequality. There's many proofs of this. But it's not really, so it's sharp. There is no way to improve it. But it is not as natural as you think. So jumping from slide 1 to slide 2, it seems that this is the only choice, but not really. If you remember what I started with, I didn't say let omega be a domain in the plane. What I said is let gamma be a Jordan curve in the plane. And then there is this domain omega. Jumping to dimension n, we have to go the other way around because the boundary topology of this omega could be very complicated, okay? However, that also says, well, maybe that wasn't the best way to generalize. We could have just go the other way and said, well, we want to stick to this Jordan curve. And this is another way you can do it, and what you end up with is what I want to call the isoperimetic inequality for curves in Rn. So now it's a completely different question, because suppose you have a curve, maybe in R3, then again you want to find something to fill this and compare area and length. But in contrast to the first two questions, there is no canonical filling in any way, right? So in the plane, there was this canonical filling. Again, if you go up in dimension, you look at the domain is the only filling of its boundary. And here, I mean, it's unclear what we want to do. Of course, we want to fill it somehow with some kind of surface, because we want a relation between area and length, and there's many choices. So I'm not going to, list all of them. Let's stick to maybe the most natural one. Maybe we want to fill this by a disk. Okay, that would be kind of the analog here. And then what is actually true is this statement, suppose now you have a closed, now I don't insist that this is a Jordan curve, so it doesn't have to be embedded, but that's a minor point. So you take a closed Lipschitz curve, the one I draw here, and then it's possible to fill this by a Lipschitz disk D, such that the area is controlled in this way. And note that this constant, well, it's the same constant as before, so it has to be sharp, right, because it's already sharp in the plane. Cannot do better than this. And again, equality holds if and only if this disk is actually a flat disk lying in some two-dimensional subspace. And I know this is a colloquium talk. It's supposed to be light, but let's prove this, because it's easy enough, and there's something you can take away. If we want to prove this, then a good idea is to make some normalizations. So the setting we look at is, so you have a curve from the circle to Rn, and, well, we can assume that it's arc length preserving. So we can assume that the derivative is norm 1 everywhere, right? This is no restriction. We just take the arc length parameterization. In particular, that means that the length of this gamma is 2 pi. And now what we are looking for is this Lipschitz disk that satisfies this area bound. And what we do, suppose this is our curve, gamma, we want to take a cone, meaning I take a point and then I take all the segments running to this gamma. Now I need to choose this cone point, and the way we do it is we take the center of mass. So after translation, we may assume that the center of mass is just 0. Okay? If not, then we move it to the side. Now, if that's true, then I can pick my cone. Let me draw it first and then write down what the formula is. It's simple enough that, I don't know, maybe something like this. I don't know how good this picture is. And, sorry. So if you want to write it down, it's a map from the disk to Rn. And if you write it in polar coordinates, it's just R times gamma. And I claim this does the job, because if you think about this, the area of this U can be estimated in the following way. So think of this point here. Maybe I do use some color here. So maybe this is gamma of t. So the contribution to the area coming from this pointer, from this segment, what is it? Well, remember, this is unit speed. So what I'm looking here infinitesimally is this triangle. Well, this side length is just the length of gamma of t, where this side length is 1. So the contribution is precisely this side length, right? If this direction is perpendicular to the position, and in general I have an inequality. So contribution here is at most norm of this. So the area of this cone is just this. And, well, this is the right thing. So, sorry, 1/2 of this. So it's a triangle, which is at most this by the Cauchy-Schwarz inequality, and then I claim this is at most pi, because here, this is at most the length of, sorry. And this is Wirtinger's inequality. It's a simple form of the Poincaré inequality. So just so what this is if you have 2 pi periodic function, and the average is 0, then the integral of, so the L2 norm is bounded by the L2 norm of the derivative. So that's Wirtinger's inequality. If you want to prove it, just write both sides as a Fourier. So just write f as a Fourier series and just write it in. Okay, so there is this simple argument that proves this isoperimetric inequality for curves. And it's actually sharp, so it's surprising. But it actually gives us something. Namely, suppose I would not have told you how to do this, but I've asked you to do it. So the task is to find some disk that satisfies this bound. If you don't know what to do, then there's kind of a canonical way to approach this. So if this holds for some disk, then it does hold for the disk of minimal area. Okay, so if I don't know what to do, maybe choose a disk that is minimal, area minimizing. Suppose there is such a thing. If there would be such a thing, then our argument already tells us, well, okay, so this is better than the cone, so it has to satisfy this inequality. But even better, not only does it satisfy this inequality, but it satisfies this inequality for all subdisks, right? If you have a minimizing disk, suppose there would, there is such a thing, maybe it looks like this, then not only does it satisfy this inequality relating the area of the whole disk to its boundary, but whenever I take a subdisk, the inequality also holds there. Because if it would not hold, I could just cut and paste one of my cones in there, bringing the total area down. Okay, so what we learned here from this trivial argument is that a least area disk, which would have been the right choice to begin with to try to prove this, will satisfy this type of inequality intrinsically, okay, inside the disk. Okay, this is potentially interesting, assuming, of course, that there is such an object. Okay, so there's 2 questions that are raised by this. So first of all, is there ever such a least area disk? And then secondly, okay, so we learned something about the geometry of this disk, namely it does satisfy this isoperimetric inequality. Then you should ask, well, are there other ways it resembles maybe the Euclidean plane? Or are there other geometric, restrictions that you can conclude from this area minimization? And obviously it is a restriction, because if you take a round sphere and you take an equator, then the best way to fill this equator is the hemisphere. And if you do the calculations, the constant that shows up is 1 over 2 pi. Okay, it does not satisfy this. Okay, so if we follow this train of thought, then this leads us to the classical Plato problem, which precisely asks this question. Suppose you have some closed curve in Rn, does there exist a least area filling? And the answer to this question is yes. And here's the theorem. So for any Jordan curve of finite length, you do find, say, Lipschitz disk of minimal area that fills this gamma. And unfortunately, I forgot to put the years here. So so they proved this independently around 1930, and this was a big deal. It is still a big deal. Okay, so Douglas won the first Fields, so one of the 2 first Fields medals for this theorem. The other one went to Alfors. Okay, so that helps us out in this way, that it says, okay, so in principle we can take this theorem, instead of making this clever cone, just take the minimal one and then say something. Well, in order to say something, we need to conclude some structure about these minimal disks. And one simple thing that you can say is coming from the calculus of variations. So here's a basic fact. Suppose you have any surface in Rn, and then suppose you have a variational field. I'll tell you what that is in a second. then the following thing holds. It's usually referred to as being the first variation formula. What it does is this. So suppose you have your surface sigma, and then by variational vector field, what I mean is just a vector field that has compact support away from the potential boundary of this sigma. So it maybe looks like something like this. And what this vector field allows you to do is move your surface. So what we can do is just flow along this vector field and produce new surfaces. Maybe let me just draw it like this. Maybe the one. And the right-hand side in this equation is just the following thing. So what I can do is for every t, I can compute the area of this surface sigma t, and then I can take the derivative at t equal to 0, and that's this thing. And this equation tells us that this first variation is controlled by a term that's geometric in nature called the mean curvature, capital H. So let me explain what this is, or at least to give you an idea what this is. To see what it is, so suppose our surface is simple, it's the graph of a function. Okay, you have some function, and then our surface sigma is supposed to be the graph. Maybe the picture looks like this. I don't know, something. This is sigma. It's the graph of f. Then to understand what the mean curvature is, what you can do is, so pick a point, x, and suppose that the gradient of f is 0 at x. So what that means is that the tangent space here is horizontal, okay? Then the mean curvature at that point is just the trace of the Hessian of f, which is Laplace f. Okay. So now you have some understanding of what the mean curvature is. And so just one comment here. So this looks like it's so the mean curvature is a linear operator. It's not the case. Okay, it's just because we chose the right way to look at it. So at points where the gradient is non-zero, this is not true. So the operator has to be nonlinear because it's a geometric notion. It's invariant under isometries, right, under rigid motions. Anyway, so what this tells us is that this mean curvature is what is responsible for the change of area. Now, if we have a minimizer, then obviously this is a critical point for area, and this h has to vanish. And from this, we can conclude something intrinsically, as we did for the isoperimetic inequality. And to use this first variation in saying that the mean curvature is 0 doesn't really need the surface to be an area minimizer. What it does need is to be a critical point, right? That's what it says here. So basically the derivative is 0, meaning h is 0. So this naturally leads to this definition of minimal surfaces, right? Minimal surface is just a critical point for the area functional. And then for those, we can say something, right? This mean curvature vanishes, and this has some meaning. And the geometric meaning was observed by Gauss. So that means that the intrinsic curvature, I didn't tell you what curvature is, I will in a minute, but for the second, let's just follow what we understand from this. It means that the curvature of the surface itself is non-positive. And what is the curvature in this simple picture? Well, so the mean curvature was the Laplace of f, which is the trace of the Hessian. So it's a sum of two eigenvalues, lambda 1 plus lambda 2. And the curvature of the sigma is the product of the two eigenvalues, right? It's the determinant of this, which of course, if the sum is 0, the product is non-positive. Okay. So at this point, I want to stop for a second. So all three topics that appeared in the title, we have seen now. and we saw some relation. So you start with the isoperimetic inequality. A natural way to try to solve it is to look at area minimizing fillings. And those area minimizing fillings, at least if we're looking at circles and surfaces, they are intrinsically non-positively curved. So I think so far that's actually an interesting fact. But this goes much deeper. But in order to explain this, I have to make a jump now. So what I will do is now I will tell you what curvature is, not Riemannian curvature, but in a more simple way, but actually more useful way. And then we go the other way around. Starting with an upper curvature bound, we want to understand isoperimetic inequalities. Okay. Here it is. So, okay, historically it went the other way around. So curvature, of course, curvature was studied for surfaces in Euclidean space, in R3. But then to actually come to Riemannian geometry, Riemann kind of wrote down an obstruction for the existence of an isometric embedding of a Euclidean ball. Okay, so Euclidean geometry is the most natural geometry, and then you want to understand, so what's the obstruction to finding actual Euclidean geometry? And what Riemann wrote down is a term second order in the metric called the Riemannian curvature tensor. And then people studied this. It's a complicated multilinear object, but from that you can extract all kind of information. In particular, you can understand like how surfaces in this space are curved. And then from this, if you assume that all surfaces are maybe positively curved, then you can understand something about the geodesics. So geodesics are shortest path between points. Okay, and what curvature does, it kind of dictates how geodesics diverge. And I'm sure a lot of you have seen these pictures. It's kind of intuitive that, you know, the smaller the curvature, the stronger the divergence. This here is the Euclidean picture. Geodesics are just straight lines, they diverge precisely linearly. This you would find on a sphere, and this you would find on a saddle surface or in hyperbolic space. Okay? So, but now if that's actually true, if that's what curvature is, then there is no way that we need some additional structure, you know, beyond the things we need in order to see these pictures. To see these pictures, you need to know what geodesics are, and you need to have a distance, right? So you can talk about divergence. And just taking that gives you, well, you cannot really define a number, but you can define a bound. Okay, you can just say, okay, I look at spaces where geodesics do not converge faster than in some model space. And this leads to this notion of kappa spaces, where the slogan is this: geodesics diverge at least as fast as in some M2 kappa. So I need to tell you what this is. And up to scaling, so kappa is a real number. It could be positive, it could be 0, it could be negative, and up to scaling, we look at the case 1, 0, minus 1. And the spaces we see is the round 2 sphere, the flat Euclidean plane, or the hyperbolic plane. And I'm sure you have seen all three of those before. And those are the spaces that you want to compare up to scaling. So once you scale your space, if you have a sphere that's very small, the curvature is very high, but if you scale it up to some unit size, then this curvature is 1. And similar, the same you can do for every kappa. You take some kappa, you rescale it in the right way, then you just see these 3 spaces. And those spaces you take as a comparison. And since non-positive curvature for this talk is kind of the most essential one, let me give the definition in the case kappa equal to 0 more precisely. So you start with some metric space, that's all you need to know, and in such a way that it's actually geodesic. So you need to know what geodesics are, otherwise you can't talk about divergence of geodesics. So just by assumption, any 2 points are connected by a curve, such the length of this curve is equal to the distance. Okay, it's the shortest distance between those points. And then it's actually convenient to, instead of just look at divergence, look at triangles. So what I see here is this geodesic space X, and I have a geodesic triangle. And since this kappa is 0 here, right, cut 0, I want to compare with this model space, the Euclidean plane. So what I do first is I draw the same triangle in the Euclidean plane, and by same, I mean a triangle that has the same side length, which is possible, right? The only requirement is that all three triangle inequalities are satisfied. Then I do find such a triangle, and there's only one. And then I can compare. And what do I compare? So I take any pair of points on this triangle in my space, then I find a set of corresponding points on this comparison triangle, which just means that the points divide the sides in the same ratio. Okay. And then the fundamental inequality that defines these spaces is as follows, right? The distance between P and Q is at most the distance that I see in the space, which means that these triangles are not thicker than these comparison triangles. And that translates to this divergence that I mentioned before. And if you just ask these things, then you get a very, very rich theory, okay? For now, it seems like this is, first of all, it's very elementary, okay? There is no deeper notion, and it's a little arbitrary. But so I cannot convince you really why this is interesting, but let me say like 2 sentences. So first of all, traditionally, the examples of cut-zero spaces come from Riemannian geometry. So non-positively curved, simply connected Riemannian manifolds are examples. And there's a huge supply of those. Some, well, the most interesting ones come from algebra, if you want, from semi-simple Lie groups, the so-called symmetric spaces of higher rank, not necessarily higher rank, of non-compact type. And all of those are examples, and they provide nice geometric models for very interesting groups, right? Lattices and Lie groups. And then you can say, okay, so that may or may not be interesting, but this works for smooth spaces. Why do you want to go away from smooth spaces? And there's many convincing reasons, and one is, okay, so if you want to incorporate other interesting groups, then there's many examples where you do find models that are non-positively curved in this sense, and these groups, they act nicely on these spaces, but we know that they cannot act nicely on any manifold. Okay, so for me, that's maybe at this point, we agreed that these spaces are interesting, and we move forward. And what we're interested in is non-positive curvature versus minimal surfaces versus isoperimetic inequalities. So let's look at isoperimetic inequalities in such spaces. And so what can you do if you have a Jordan curve in such a space? So in order to explain this, maybe let me go back to this again. Let me maybe mention 2 immediate consequences of this maybe strange inequality. The first is that in any such space, not only are there geodesics between any 2 points, but there is precisely one. Okay, geodesics are unique. And why is that? Well, suppose you would have 2. Then I choose an additional point. Now I need to write down a comparison triangle in the plane. This comparison triangle looks like this, right? But now in my space, the triangle should be thinner than in the model space, but already in the model space, it's infinitely thin, right? It's just a segment. So that means geodesics are unique. And once you have unique geodesics, that tells you that you have some kind of continuity. Once you have some continuous object, you can kind of cone it off to get something continuous again. And from this, you can conclude that all these spaces are contractible. And the reason is the same reason why Rn is contractible. You pick your favorite point, and any other point, you just move it towards your base point along the unique geodesic. So those can branch in some way, could look like this, but what you're doing, you move everything along these geodesics. Okay, that will contract your space. So this explains why these spaces are interesting in topology and group theory. Okay. So, but the point I wanted to make is really this. You have these unique geodesics. And now let's see why this helps to understand something about isoperimetric inequalities. So just like before, we start with the Jordan curve. Now in some of these non-positively curved spaces, and what we can do is we can take a cone, just like in this picture. Now let's see what the area of this cone is. If you look at one of these cones, so this is not really a cone, I just, drew an inscribed polygon, and then let's estimate the area of that. well, what is the contribution of this blue triangle? Well, the triangle is not thicker than the Euclidean triangle, so the area is at most the area of the Euclidean triangle. So to estimate this, well, the area is at most A times the length of this. But this segment here joins 2 points on the curve gamma. So the length is at most, well, the length of gamma maybe, or 1/2 the length of gamma. But let's not be greedy, let's just say the length of gamma. If you add this up, right, this is a polygon inscribed in the original curve. So the length of the polygon is most the length of gamma. So what we end up is something that is quadratic in the length. This is a little small. What I wrote down there is filling of gamma is at most some constant times length of gamma squared. So this is not the Euclidean isoperimetic inequality, but the quality is the same. It's a quadratic inequality. But now something interesting happens. If we would do the same thing in negative curvature, where still geodesics are unique, because in the hyperbolic plane they are unique, if we do the same argument, then we get a different answer. You can already see the answer here. This filling, the area of a disk filling this, is linear in the length of gamma. And the reason is that if you look at one of these triangles here, so in the Euclidean case, the contribution was basically A times the length of this. And I'm claiming that here the contribution is just basically A. And the reason is basic hyperbolic geometry. So you don't need to know anything about hyperbolic geometry. I'll just tell you in picture what's going on. So if this is the hyperbolic plane, then the crucial thing about the hyperbolic plane is that there are ideal triangles, and the area of such an ideal triangle is pi, which is not important. The important part is it's finite. So if it's finite, then what that means is if I take any triangle, let me draw this picture. And the triangle that we're considering is this one. Maybe this is the side length A. Then from the picture, I'm sure you believe, the area of the small triangle is at most the area of this triangle that has one vertex at infinity, okay? But then this is part of this large triangle, which is finite area, and the proportion of the area that this one triangle is, it depends only on A, okay? So that means in a hyperbolic triangle, I can estimate the area by the smallest side length, okay? And if you do that here, then this is precisely what happens. You have some constant times A, but then if you add all those A's up, you only get the length of gamma, okay? So then this is, right. This is interesting, okay? Not only do those non-positively curved or negatively curved spaces admit a quadratic or some isoperimetric inequality, but the quality of the inequalities sees the difference between non-positive and strictly negative. And in a drastic way, you go from quadratic to linear, okay? So once you have something like this, you should, well, you can ask, what is really going on? And you want to know what, if there is something more precise. And this simple argument explains something, but it's far from the truth. So to see what is actually true, I want to state this old theorem of Reshetniak, which was basically, I think cut spaces were basically found by Alexandrov around 56, so maybe 10 years later, 12 years later, he proved this. And it's a remarkable result. So the statement is here, but it's a little long, so maybe don't read it and just listen to me. I will put it down in a second. So what it says is, whenever you have a curve of finite length in your cut space, so then what you can find is a convex set in the model space. Let me just do the plane, the Euclidean case. What it means is, I start with some curve gamma here. Then I can produce a convex set in the plane and a map F, which is one Lipschitz, such that the boundary of this convex set gets mapped to gamma in an arc length preserving way, okay? So what this means in particular is that the area of F is at most the area of C, right? Because it's one Lipschitz. Length goes down, so in particular area goes down. But now we're in the Euclidean plane, okay? So the classical isoperimetric inequality tells us this is at most 1/4 pi, the length of the boundary of C squared. But remember, these majorizations provided by Reshetniak have the property that on the boundary, they preserve the length. So this is really equal to 1/4 pi times the length of gamma squared. And if you put this together, then what you see is not only a quadratic inequality, but it's the quadratic inequality with a sharp constant 1/4 pi, just like in the plane. Okay, yes?
Yeah, I mean, how to prove, how to construct the map F here?
This is the content of the theorem, that this map exists. It's a theorem.
Did you got kind of a constructive proof of the existence of some space, or did it constructive proof of the existence of
the way it's proven is this. So first, you need to prove it for a triangle. If you can prove it for a triangle, you're done. But to prove it for a triangle, it's not the map that you think. The map you think is this. You just take the cone, right? This you can do. But the point is, this is not one Lipschitz. Has the right area, it's not one Lipschitz. What you need to do is basically have to take a reparametrization of this map. And the way to do it is, so you, in your space, you take this triangle, but then you take a very fine subdivision here, and then you take these segments, and for each of those, you choose the comparison triangle, and you glue those together. So what you see doesn't really look like so this thing would basically say you start with a Euclidean comparison triangle and take the map. That doesn't work. But if you make this fine, you change basically this triangle to something that looks like this. If you make this fine enough and pass to a limit, this is how to get it. But what it really is, you do take the comparison triangle and you map it to this, and you do map the radial geodesics to the geodesics here, but not with the constant speed parameterization. So the theorem is actually a theorem. It's not. And okay, so I should say, I said once you did the triangle, you're done. The reason is this: so once you did a triangle, you can basically do an induction and to do a polygon. Right, you just do an induction on the number of edges, and then you pass to a limit. This is how you get it. But it's not, yeah. It is a theorem. Okay. And, okay, so as I said, and if you notice, so I only drew the thing for kappa equal to 0, and the way it's stated here really only works for kappa 0 or negative, because if it's positive, you need the curves cannot be longer than the equator in the sphere, but let's ignore this. So, but still, it works for every kappa. So that means, by the same argument here, so getting this one Lipschitz map tells us that the isoperimetic inequality kappa space is at least as good as in a space of constant curvature kappa. So also a negative curvature, okay? So what did we learn now? So for a non-positively curved space, the isoperimetric profile behaves as you maybe wanted it to behave. Yeah, it only becomes better. Negative curvature helps you to find fillings of even smaller area. So maybe the story should end here, but it doesn't. It actually gets interesting now, because you can go the other way, which is somehow surprising. So here's a result, and it's rather, well, 2018. The statement as stated is actually from 24. So it tells you that not only do cut kappa spaces satisfy the same the same isoperimetric inequality as the model space, whenever you have any geodesic space that does satisfy the isoperimetric inequality. So here, again, so what does it say here? So it says, I take any geodesic space, and then suppose every Jordan curve can be filled by a Lipschitz disk such that the Euclidean isoperimetric inequality holds. Then that means it is a cut zero space. So just to be clear here, this inequality does not see geodesics, okay? There's area and there's length, that's it. The definition of a cut space requires you to, first of all, understand what geodesics are, okay? And then point-wise estimate the distance on these geodesic triangles. So the way you should think about this is basically going from an integral bound to a pointwise bound, which is just usually impossible, okay? But here that is actually true. And the theorem is kind of it's maybe the latest outcome of minimal surface theory in metric spaces. So Lichak and Wenger developed this large theory of minimal surfaces in metric spaces, starting with solving the Plato problem in any complete metric space, and then developing a whole theory that basically allows you to understand the intrinsic structure of such a minimal disk so well that you can prove this. And this is not only kind of nice for people that are interested in this, it actually says something deeper. It says that this cut theory is as much an analytic theory as it is a geometric theory. You don't need geodesics, okay? You don't need angles. You can just work with Sobolev disks instead. Okay, but maybe here it should stop. But, and it kind of does, you cannot improve this in any way. So you can ask similar questions, but all these similar questions are answered here. So you can look at you can say, okay, maybe there is a stable version of this. Maybe you have a quadratic isoperimetric inequality, the constant is maybe not 1/4 pi, but it's kind of close. Or you have a sequence of spaces where the constant gets closer and closer. Well, then the thing that you expect is actually true. So the limit space is cut zero then. Or there's a localized version, suppose you only know this quadratic isoperimetric inequality for curves of length at most 1. Well, then every ball of radius 1/2 is cut zero. So any question you can ask, the isoperimetric profile sees it. But there is one thing that's not covered by this. Namely, you could ask, you do not compare to a model space, but just, kind of naively ask, well, what if I wiggle in this constant at all? I don't see something, let's just put something here. And if you put something larger, then you would think the space allows for positive curvature. If you put something smaller, then it's absurd. Putting something smaller, there's not really a space that satisfies this. However, there is some wiggle room. Namely, you can put a smaller constant and then just ask it to be true for maybe very long curves. And this falls within the realm of maybe coarse geometry or asymptotic geometry, which is interesting in relation to group theory and something that I'm kind of working on intensively. And this is where I want to take this discussion now, because in the end, I kind of want to tell you about my actual latest results. So this is the result in this direction. So let's see what it says here. Suppose you have a geodesic space again, and you ask something about the isoperimetric inequality. What you ask is that, notice here, so here it says, for every long, okay, what it explicitly means, suppose there's some constant L0, and then you only look at curves that have length at least L0. Then suppose all of those you can fill better, right? There's this definite epsilon. You can fill them better than you would in a Euclidean plane. Then what does that mean? So what it means is there should be some negative curvature, right? Better than Euclidean has to come from some negative curvature, and it's a definite statement. The space is Gromov hyperbolic, and it's very simple what that means. That means there exists some delta such that every geodesic triangle is uniformly thin. So that means this picture, okay? And that's somehow, well, notice this result is older than the other one, and the proof is also somewhat simpler. But in combination with the other result, it kind of gives you a complete picture. If you have a quadratic isoperimetric inequality with constant 1/4 pi, the space is cut zero. If it's a little better, then automatically you jump to a Gromov hyperbolic space. All triangles are uniformly thin. And from this, it actually follows that the isoperimetric inequality is linear. Okay, so remember this simple argument that I gave, where in a cut zero space, you see this kind of Euclidean cone picture, where in negative curvature, you see something that maybe looks more like this, where you have these strongly curved triangles. And this led to a quadratic isoperimetric inequality, where this led to a linear isoperimetric inequality. The only thing that we really used here is that some assumption on triangles, namely this. So uniform thinness of triangles. Okay? And this is a very interesting phenomenon. This is why it's called a gap or isoperimetric gap theorem. you look at this constant, and once it drops a certain threshold coming from Euclidean space, then the geometry is drastically different. Okay, and this, once you see something like this, you want to see what's the reason for this and what's maybe the general phenomenon. And it's rather hard to see what the mechanism behind this is, so it needs it needs someone clever to say what's going on. And Gromov explained what's going on. So there is this notion of asymptotic rank, which I will explain now here. And what Gromov says is what we're seeing here is the first instant of this isoperimetic gap phenomenon, which comes from the geometry, the large-scale geometry of non-positively curved spaces. So in order to explain this better, I need some blackboard. So I'm guessing the part of the talk that's generally accessible is over. Still, I want you to just, don't hold, if you have questions, just stop me and ask me.
Actually, can I ask a question about it?
Yes.
This was about long German, long German curves.
Yes.
So this is sigma global structure. Can it have?
Sorry?
So this means a global structure statement, right?
This means it doesn't say anything about small scale. It doesn't say any. No, you don't. So here's the point. So it's unclear what a large-scale version of non-positive curvature is, but it's completely clear what a large-scale version of negative curvature is, and this is notion of Gromov hyperbolicity. So let me say this again, and I think the confusing part is delta. So you should think of delta as a huge number. And Gromov hyperbolicity means that whenever you take a triangle, then every side is contained in the delta neighborhood of the other two. So if delta is just huge for small triangles, there's no information at all. Okay? But depending on delta, which is 1 million, right? If you then take a triangle of size 1 billion, then it is a restriction. And the restriction is the triangles look like this. They're very thin.
Okay. So it means there is no notion of curvature on small scales?
There's no notion at all. So curvature would mean you can assign a number to maybe a small disk. So that's out of the question. But what you can say is, right, the way triangles look. And they resemble, so in negative curvature, they are uniformly thin. So in this uniform thinness is something you can express in complete generality, and you can express it in this nice way that just doesn't see small scales at all. And the statement is basically that you can also, this other thing, having an isoperimetic inequality for long, maybe very long curves that is better than Euclidean is really just the same thing. But again, you have to somehow, there's some trick to move from curves to geodesics, because those are geodesic triangles. And the thing that is happening is, maybe I can explain this a little better now. So because this thing is a generalization of what we saw before. So maybe it's a good idea to explain the case k equal to 1 better, which is really this one. So the point is that, so first of all, I need to tell you what this asymptotic rank k means. So what this should mean is that the space intuitively means that the space on a very large scale looks k-dimensional. This is what it is. But let me make this precise at the simple example of a hyperbolic plane. So you take a hyperbolic plane, and as a characteristic, I draw this ideal triangle. This is how geodesics look. This is somehow what you should think of. Now, if I want to look at a very large scale, in order to look at this scale, I could rescale my space, make this large scale 1 billion to the scale 1. That means I multiply all length by some number lambda. And the new picture I see looks like this. Okay, the distance was here, it was 1, and here it's lambda, where lambda is a tiny number. Okay? So now there's actually a way to produce a limit. And what does this limit look like? It's a tree. And the tree actually branches everywhere. To see that there is some branching, just focus on this central point. If you focus on this point in the limit, so, okay, I didn't tell you how to produce this limit, okay? But the limit has the property that distances of finitely many points will converge to distances of finitely many points. In particular, what I can make sense of is limit of geodesics will be geodesics, because I can, to see that the limit of a geodesic, I only have to look at 2 points, okay? So all of these geodesics will converge to geodesics, but on the other hand, the distance from the central point to the sides goes to 0. In the limit, I see this ideal iPod, okay? And actually, this happens everywhere. So this explains that this construction is called an asymptotic cone construction. It makes use of some logic device, but that's not important. The point is there's some weak limit, and this weak limit in this particular case of a hyperbolic space is a tree. It's a tree that branches everywhere. So this is terrible space. It's not locally compact or anything. But what it is one-dimensional. In any reasonable sense, it's one-dimensional, okay? And what does that help me? Well, suppose we want to answer these questions. Suppose we want to say that in this setting, we want to say something about the isoperimetic inequality. Well, the way you should think about this is as follows. If you take a huge curve, so a very large curve, okay? So then if you rescale, the curve becomes smaller, okay? And in the limits, if this limit is at least strong enough to somehow model the geometry of the space on large scales, then such a circle, should feel like living in this limit space, which is a tree. So it should look like this. Almost completely degenerate. Okay? Because in the limit space itself, it's a tree. There is no circle. There is no embedded circle. Every circle is completely degenerate. Its filling area is just 0. Okay? So then if you believe in some kind of continuity, then you would say, okay, so if that's a good model, then the filling area of this limit thing, which is 0, should be close to the filling area of this. Okay, so the filling area of this should be then some small epsilon. Unraveling this, okay, just tells you what you wanted to know. Well, almost. What it tells you is that, what does scaling mean? If I multiply by some lambda, then the length of this is multiplied by lambda, but the area is multiplied by lambda squared, okay? So that means the filling, so from this picture, you can conclude that for large circles, the filling area is subquadratic, okay? Because if I rescale by lambda, I change it quadratically, but then it goes to 0. So the filling area is subquadratic. And then there's a second argument that says that whenever you have a subquadratic isoperimetric inequality, you have a linear one. This is not trivial, but it basically depends on the fact that you're just looking at circles, and there's a good way to cut circles down in a clever way. Okay? So could you take something from this picture? Yes?
So why don't you, when you do the, okay, in the singular space, so why don't you make a kind of a stratification of the singular space, and then you do kind of develop some inequality in some stratification inequality that you glue back together?
It's one idea.
Yes, I'm thinking, yes.
Yeah, I mean, right, it's an idea. Why not? But so let me just point out, so it's 91, and the conjecture is central. So there is something we know about this. Okay, so sorry, this is the case k equal to 1. Okay, the general case k, use your intuition. So the space somehow on large scales should look like something k-dimensional. If you have a k-dimensional space, then there is no non-trivial k-cycle. That's just topology. Every k-cycle is 0. And then the same kind of intuition, right? On a very large scale, the K cycle should feel like it lives in something K-dimensional, so it should be completely degenerate. And then if you unravel this, this should mean that the filling volume of a K-dimensional cycle on a very large scale, it should be much smaller than what you see in Euclidean space. Okay? And this is precisely the content of Wenger's theorem. So here that's precisely what it is. So suppose you have a Cat-zero space of asymptotic rank at most K, then the filling volume is little o of volume. So what that means is precisely this. So if you have a cycle of very large volume, a K-dimensional cycle, and the volume is huge, then you can find a chain Y that fills this such that the volume of this is at most epsilon times the volume of Z to the correct power, yeah, which is K plus 1 over K. Okay? Does that make sense from this picture, right? So if you rescale, then this is a scale invariant inequality, okay? If you rescale, then you should be close to the K-dimensional space, which means your filling volume should be close to 0, is epsilon, okay? So that's the intuition. The actual proof is hard, but that's the intuition. Okay, and as I explained here, to get the linear isoperimetic inequality for curves, you could go in this way. Step 1, you make this asymptotic argument to say that the filling area is subquadratic, and then there's an additional argument to go from subquadratic to linear. And in Stephan Wenger's ICM address, he basically said, no, he exactly said that he was hoping that this is step 1, okay? To prove Gromov's conjecture, step 1 is proof that it's sub-Euclidean, and then you need the step 2 that goes from sub-Euclidean to actual linear. But, well, this is still missing. However, we did make progress last year. And this is the theorem that I wanted to state. It's a lot, but let me just explain. It's precisely, it's close to what you want. But it's a little better in some respect and a little worse in another. So first of all, here, I look at a slightly different case. So first of all, notice now we move up in dimension, okay? I'm not looking at circles, but I look at 2 spheres. And I want to fill 2 spheres by 3 balls, the most natural thing. And I want to do it in an efficient way. And the theorem says that 3 things are the same. The first thing here, you don't really need to read this. I think I can explain this. So suppose you have this filling inequality for 2 spheres. So S hat is a 2-sphere filled by this 3-ball B hat. Suppose you have this inequality. So remember, you should notice the resemblance. Yeah, 1 over 6 square root of pi is the sharp constant. Okay. Then going a little better, having a slightly better constant here, then that should mean that you're actually linear. We cannot prove this. However, what we can conclude from this is that for every delta, the filling inequality has actually this form. Okay, it's not linear, but it's almost linear, apart from this annoying delta. We can make this delta as small as we want, but that forces us to increase the C. You understand the statement, yeah? For every fixed delta, I find a fixed C. And once I look at very large ones, the delta becomes more powerful. And the statement says, well, these 3 things are equivalent, so I never really told you the precise definition of this, and I don't want to, but I think I gave some idea what this asymptotic rank at most 2 means. Okay, but to come back to the point I said, it's also a little better. So Gromov's conjecture was about integral cycles and integral chains, so you don't care about topology, which is somewhat, so at least group theorists usually are not happy with this. Here we can kind of say, this is the actual natural thing. You take a sphere and a ball. However, I kind of, cards on the table, this actually plays in our favor. Because if I would not insist on this being a 2-sphere, then we cannot prove the same thing. But we can prove something a little weaker. then you could ask, okay, so now let's not look at two spheres, let's look at a torus, or let's look at some surface of higher genus. What about those? They are maybe not that natural, but if you can do it for the sphere, maybe you can do it for all of them. And we can, but in that case, so what do you do then? You take some surface of genus G, so the Lipschitz image of such a thing, you pick some model metric, and then you look at Lipschitz maps from a surface of genus G, and you want to fill it by a handle body of genus G, right? That's the natural filling. Then the thing is that we can show that the volume of the handle body of genus G that you need in order to fill this is at most C, and now the constant depends on delta and G, unfortunately, times the area of the original surface to the power 1 plus delta. Okay. So now if you go back to Gromov's actual conjecture, apart from the fact that we cannot really prove linear, in his statement, this constant should certainly not depend on the topology. And you could ask, okay, can you maybe get rid of this? And at the moment, we cannot. I mean, we can prove this, but again, so it depends on the genus. I didn't say when this, so this is from this year, from February, and then tomorrow we will post this. So there is a way to get rid of this dependence. So here we really, now we forgot about the topology. It's not spheres, but general K-cycles and fillings by K+1 chains. And then we can produce this delta isoperimetric inequality, but there is some assumption. Namely, there's some technical assumption that's called asymptotic Nagata dimension. I'm not going to define it, it's just any finite dimensional K0 cube complex satisfies this any Euclidean builder. So it's not well understood so far, but there's many natural examples. If you would ask me, I think if we really push, we could maybe get rid of this, but that's maybe not the priority. What we really would like to do is go from dimension 2 to any dimension. Okay, thank you for your attention.
Very nice talk. Do we have more questions?
This last remark reminds me of the Douglas problem for minimal surface.
Yes.
Relation to existence of
It's not really related. So the Douglas problem asks to, so you have not one Jordan curve, but you have a couple of Jordan curves, and you want to, this we can solve in metric spaces in the same way, but you need this Douglas condition. The Douglas condition asks this strictly better, yeah. Yes, exactly. No, but this is generalized to, but here the filling is really the three-dimensional thing. So if you want to minimize, you would minimize this. The handle body is the three-dimensional filling of the higher genus surface. So if you think about minimal surfaces or minimizing currents, the thing that you would want to choose minimal is this, which is higher dimensional.
The Douglas problem has something to do with the existence of minimal surfaces with prescribed genus. No?
Exactly, yes.
And in fact, this reminds me, because Seifert was very much interested a long time ago, and I had stated that it's not really proven they exist.
Really? Okay. Yeah, okay.
But he went home and came back to the Nachsitzung and said, I saw that they exist, that he gave a proof, but not by variation, but by deformation.
Oh, really? Interesting, very interesting. Okay.
Very nice.
Oh, by the way, so I will take questions in a second again, but I forgot a very important part. I did not tell you how this thing is proven, because it's impossible to tell, but the crucial new ingredient that we needed and that we used to prove this delta isoperimetric inequalities is what we call a minimal tetrahedra. And yesterday, I tried to produce a picture of a minimal tetrahedra using some computer program, and I failed because I'm not very good at that. So I asked ChatGPT to produce this picture, and then After some time, I asked if it is still working on the picture, and then it told me that I ran out of computer time for the picture. So I failed to show you what a minimal tetrahedra looks like. But Petra was so kind to show me a beautiful geometry lab, and here it is. Okay, so a minimal tetrahedra, let me just say at least what I meant to say is a crucial, the proof, so we try to fill this piece by somehow with some elementary blocks, and the key thing is what we call a minimal tetrahedra, and it's the following simple thing. You take 4 points, and then you take 6 geodesics, and then the sides we fill in by minimal disks, okay? And this is what we call a minimal tetrahedra. And the key upshot is that such a minimal tetrahedra, if you are in asymptotic rank at most 2, does satisfy a linear filling inequality. So this we can show. That's the key new ingredient, okay? That's what is behind the proof. And
everybody can come to Hegel and look at the beautiful minimal tetrahedra. Do we have another question for our speaker? No? Okay, further questions I think can still be asked by just coming to the front and asking directly, but thanks everyone for participating, and also thanks again for the very nice talk.
thank you.